In the last lesson,
Mm.
we were looking, we were under the topic of organic chemistry, under the branch of organic chemistry, and our main aim, we are looking at alkenes, whereby
Okay.
we, whereby we looked at the structure of alkenes.
Mm.
And from there, we looked even at the nomenclature, and even we talked about hybridization. Yeah.
Okay. So the structure, nomenclature, and then we also talked about hybridization. And specifically, I believe we just focused hybridization on of alkenes. Which kind of hybridization do alkenes undergo, Gilbert?
Yes, sir.
Which one? Which kind of hybridization did we talk about that alkenes undergo?
SP2.
SP2. Very good. Thank you very much. Let's clap hands for Gilbert for that wonderful
Isaac, I
Okay.
think we are set.
Yeah, now it's okay. Thank you very much. Okay, sorry about that interruption. I believe now we can be able to view the screen. Gilbert I left when Gilbert had finished sharing with us uh, what we learned last time, and I believe we're able to see the screen. If you can see the screen, please let's use those reactions so that I can be able to know that you're hearing me and also you can see the screen. Let me see that. Okay, thank you. Okay, so Gilbert had already shared with us what we learned last time, that we looked at alkenes, its structure or structure of alkenes, the nomenclature, and then hybridization, where we are very specific, and we talked about the sp2 hybridization. We also had someone who wanted to share with us something else that we looked at. Let's put up the hand, and then we can move on to what you want to share today. Any other person to share with us what we looked at last time? Okay, so if you don't forget also, okay, I can see Nanyombi. Nanyombi, you can tell us.
Okay, well, it's Nyombi. We also looked at isomerism of alkenes and also the conditions.
And also?
The conditions.
The conditions for?
Alkenes.
Conditions.
Yes, where we looked at the presence of a carbon-carbon double bond.
Okay. Okay, I guess so. We looked also
and
at
also the types of isomerism.
And also the types of isomerism. Okay, thank you very much. So that is nice. And we said now today we shall be looking at specifically at the chemical properties. You can mute now, Ruth. You can mute. Thank you. So today we are going to look at majorly the chemical properties of alkenes. And then at the end of this lesson, we shall also be able to have one scenario item, which we shall be going through, applying all the work that we studied in the previous lesson and what we're going to be looking at in this lesson. And as I said, if we have any inquiry, any issue, let's keep on using the chat section, and also we keep on raising up our hands. So chemical properties of alkenes. Let me have one person to read for us those 2 points by show of hands. Who can take us through the first 2 points? Okay. Yes, Jovia. Okay. Jovia Sara. Okay. Baswari, you can unmute.
Sir, good afternoon.
Good afternoon, sir.
Okay,
Good
let me have
afternoon,
Sarah first, and then Sarah, you can take us through then.
So the chemical properties of alkenes.
Okay.
The first one, alkenes are highly reactive hydrocarbons than the alkenes, and their functional group is a carbon-to-carbon double bond. Then the double bond consists of one sigma bond, which is strong, and the one pi bond, which is weak and easily broken.
Okay. Now, there is one point you keep your microphone on. You have read for us that alkenes are high reactive hydrocarbons than alkanes. Why do you think alkenes are more reactive than alkanes? This statement. Sarah, you can take us through that. Why do you think they are highly reactive?
I think they're highly reactive due to the strong sigma bond between the carbon to carbon double bond.
So they are more reactive because of the strong sigma bond?
Yes, that's what I think.
Okay. Okay, thank you. Let's have also Shadia. Shadia? Okay, Shadia, you can unmute.
Excuse me, sir.
Yes.
I think they are very reactive just because they are saturated and they have that pi bond, so they are able to react.
They are
They are unsaturated,
unsaturated.
so that is why they are very reactive.
Okay, so what makes them more reactive is because of the unsaturation.
Yes, sir.
Okay. Thank you. So we are saying that what is making them more reactive? Is it because of only the unsaturation? Okay, so you're telling us yes, no. Okay, let's also see someone else who can share with us. Thank you. Let me have Gilbert. Yes, Gilbert.
I think the alkenes are more reactive than alkanes because when you look at the alkenes, they have a double bond. So is that double bond is made up of two bonds. One is sigma, another one is a pi bond. So
Mm.
the pi bond, the pi bond is we know that the pi bond is weaker than the sigma bond. So during the reaction, it is very easy to break up the pi bond found in the alkenes, hence making them so reactive because that pi bond it has what you call the pi electrons. So these pi electrons are highly they can be easily used or they can easily attack the electron deficient species, making the reactive to be easier than the one in the alkanes.
Gilbert, your name is Gilbert.
Yes, sir.
Okay, thank you very much. I think that was a very good explanation, which and is telling us that it's because of the double bond, and is continuing to tell us that this double bond it consists of two bonds, where one is a sigma bond, and then the other one is a pi bond. The sigma bond very strong, and has told us that the pi bond it is weak, and therefore it can easily be broken. So these pi electrons are the ones which are responsible for the high reactivity. That's why in the NB, we can see that we are saying that the pi bond is responsible for the high reactivity of alkenes, especially the addition reactions. So there are another point that the pi electrons are therefore attacked by electron deficient species, and for this reason, they undergo electrophilic addition reactions. So that is those are the two key points that we could be able to see under the chemical properties of alkenes. And we have seen that they are very reactive, and what makes them more reactive is because of the presence of the double bond, which consists of the two bonds, the sigma and the pi bond. Okay, there's someone who has a hand up. Yeah, I would like us to move to the next part, but after hearing from Anita. Anita, what are you saying? Okay, Anita's hand is now down. It's all right. So we can now move on. I would like to ask one question. Which name is given to electron deficient species? Electron deficient species. Anita's hand is up. Yes, Anita? Anita, you can unmute.
Excuse me, sir.
Yes, please.
I would like you to explain me more about the pi electrons and therefore attacked by electron deficient species. That part I've not understood very well.
Okay. So you'd like to know more about pi electrons.
Yeah.
Okay, you keep on mic. So Anita, when you talk about
Yeah.
pi electrons, last time in our first lesson, we looked at hybridization. And through the hybridization, which we say that for these alkenes, they undergo what you call the sp2 hybridization. And it is through this hybridization that we're able to see that the sigma bond and the pi bond form between the carbon to carbon atoms of alkenes. So the pi bond and the sigma bond, the pi bond is very strong compared to the pi bond. And you recall each bond is made up of a pair of electrons. So when you talk about a sigma bond, that is a pair of electrons. And when you talk about a pi bond, that is another pair of electrons. So we are saying that this pi bond is the one which is responsible for the high reactivity of alkenes. Why? Because it is weak and therefore it can easily be broken. So during the reaction, the pi electrons are the ones which are attacked by electron deficient because they can easily be broken and therefore they are exposed. Therefore, they can easily be attacked by the electron deficient, the species or substances which are yearning for electrons. We are going to look at that as we go to our next lesson. As we go to our next slide, we shall be able to look at those species which we call the electron deficient and those ones which are electron rich. And I've seen in our chat, someone is telling us electrophiles, and then another one telling us the nucleophiles. So in our next slide, we shall be able to see the electrophiles and what the nucleophiles are. Anita, are we okay there?
So, sir, the pi bond is the one that is related to saturation, eh?
Uh-huh. So you're saying, is the pi bond the one related to saturation?
Yeah, of the alkanes being saturated because of the double bond that they are possessing, that they can be easily broken down, eh?
No, for alkanes they are saturated, while for alkenes, for them they are unsaturated. They are unsaturated. For them they have some free electrons present. Those ones for the ones which form the pi bond. That bond is the one which is responsible for the unsaturation in alkenes. Are we there?
Okay.
Then when you go
So
to
the
when you go to alkynes, for them they have two pi bonds, which means alkynes then become even more reactive because they have two electron bonds which are having pi electrons that are also weak. Therefore, they can also easily be broken. So the pi bond, the pi electrons are the ones responsible for the unsaturation in the alkene and also in the alkyne.
okay, got it. Thank you.
Okay, someone is asking, What about the hybridization we talked about? We couldn't go to hybridization before we finish alkenes, and therefore we shall be able to see by the end of this session, we have said in our next lesson shall be tackling only hybridization plus also scenario items in regards to what we have covered in the alkenes and also in other topics. Okay, thank you. Unless we have any other question, we can be able to move on. If you have any question, please keep on putting in the chat or you raise up the hand. So we are coming to, we have seen that in that point number 2, that the pi electrons are therefore attacked by electron deficient species, and for this reason, they undergo electrophilic addition reaction. And here is that question. What is an electrophilic addition reaction? Jovix, thank you. Jovix saying electron deficient is also called electrophile. Thank you very much. We shall be able to see all those examples of electrophiles and nucleophiles. Who can first tell us, what do you understand by that? An electrophilic addition reaction. Because we are saying that alkenes, they undergo this kind of reaction. And before you go through it, we need to first understand what is electrophilic addition reaction. I'm seeing Daniela. Daniela, you can unmute. Daniela, yes.
Good afternoon, sir.
Good afternoon.
Well, an electrophilic addition reaction is that reaction in which an electrophile adds to an alkene or alkyne to form a single product.
To form a single product. You have said where an electrophile
or electrophilic reagent adds to alkene or alkyne to form a single product.
Okay, thank you. So you're saying that we are adding an electrophile to an alkene to form a single product. What is the property of the product which is formed? What is special about that product that is formed?
I think it should be saturated.
Very good. It is saturated. Very good. That is good. So, which means we are having an electrophile adding up to an alkyne. An alkyne is unsaturated, and then the final product is now becoming saturated. Thank you. Thank you. Daniela, thank you for that submission. Jovix, you have a hand up. You can tell us. Yes, Jovix.
I think an electrophilic addition reaction is a reaction in which an electrophile adds itself across a multiple bond of alkenes or alkynes to form a single product with no loss of any atom.
Very good. You have also added another word, with no loss of any atom. So in electrophilic addition reaction, we don't see any loss of any atom or of any molecule. Thank you. You can keep your microphone on and read for us this one.
An electrophilic addition reaction is that reaction in which an unsaturated organic compounds, such as alkenes or alkynes, combines with an electron deficient species in brackets electrophiles to form a single product which is saturated.
Which is saturated. Which is almost the same as the one you have given us, only that you have added for us another key point or key one, that during electrophilic addition reaction, there is no loss of any atom or molecule. Thank you very much. Now, let us look at the list. They are saying, can you list some examples of electrophiles? Examples of electrophiles and examples of nucleophile, and also understand what nucleophiles are. From this definition, we have seen that electrophile can be electron deficient species. Electron deficient. What is a nucleophile? Do you have a hint on what a nucleophile is? Yes? Okay. Okay, we can have another person. Teddy. Yes, Teddy. Yes, Teddy.
A nucleophile, a nucleophile is electron deficient species.
It is what?
A nucleophile
Mm.
is an electron deficient species.
Hi, your network is not clear. If you can be, change your location or you speak again. Yes. Okay, someone is saying electron rich species. Okay, good. Electron rich species. Okay. Then we have seen electrophile is electron deficient. And someone in the chat was telling us what deficient means, lack. So which means for these ones, they lack electron. They are deficient. When we talk about someone is deficient of maybe a particular nutrient, which means he lacks that particular nutrient. So they are electron deficient species, while nucleophile, for them, they are electron rich species. Okay. Um, we have Daniela, you still have the hand up. You can unmute. Daniela?
Yes, teacher.
Yes, please.
No, it's okay.
It's okay.
Praise.
Okay, now keep your microphone on and then read for us what is down here. You give us an example of an electrophile.
Okay. An electrophile, these are positively charged atoms which attach the region of high electron density, or they are electron deficient species and are said to be electron loving.
They are said to be electron loving.
Loving.
Okay, so I believe in this definition we have added a few key ones. Number one, we are saying that electrophile, they are positively charged atoms. And they are saying that they attach to the region of high electron density, which means they are positively charged and they move towards where electrons are. They attach to a region of high electron density. Or in other words, we can say they are electron deficient species, species which lack substances or species which lack electron. And they are adding a one, they can also be said to be electron loving. They are electron loving, therefore they move towards where the electrons are. Can you have some examples? Number one is what? Daniela, you still there?
Yes.
Number one.
Yeah, I'm not very sure, but is it a sulfite? Okay,
Uh-huh.
I'm
You
not
recall,
sure.
we are saying that they are positively charged atoms. Okay, we can give another person a chance. I'm seeing in the chat people are putting a number of them. That is good. Let me have Samsung S. Samsung you have put down. Teddy. Yes, Teddy. Teddy. Okay. Jovia Sir. Teddy, you are there.
So I'm not very sure, but
Yes,
I think zinc is one of the electrophiles.
Like which one?
Zinc.
He's saying zinc. Okay. We are saying that the positively charged atoms which attach the region of high electron density. Who is that one who was telling us? Sarah, are you the one? Okay, we can have some of them. We have like hydrogen ion, which is positively charged, and therefore it removes towards the high electron density or the area which has electrons. Number two, we can have ammonium ion. We have ammonium ion. Good. Robert, thank you. That is good. We can have someone is telling us nitrous ion, which is having also a positive charge, and also plus others which may have a positive charge. Someone is also putting for light hydrosomium ion. So those ones, what we are saying that electrophile can be those species which are positively charged and they attach the region of high electron density. Then we can also talk about nucleophiles. Who can read for us? Nucleophiles. What are nucleophiles? By show of hands. Very fast to read for us this statement we have. Okay. Okay. Shalom Kadu. Shalom Kadu. Okay,
A
good.
nucleophile is an atom or group of atoms with negative charges or lone pairs of electrons which attack the region of low electron density. They are said to be electron-rich or nucleus-loving species.
Can you give us examples of such species?
Can ammonia work?
Ammonia. Ammonia, it has some lone pair of electrons. You recall here they say a group of atoms with negative charges or lone pairs of electrons. So even ammonia works. Can you, which
Water.
thing can give us water? Good, with some lone pairs of electrons. Juliet, that is nice. Juliet also is giving us hydroxide ion. Okay. Yeah, that is nice. Many people are giving us a number of them. Someone has also put chloride ion, and also you can say ETC and more others. So those ones which are having a negative charge or lone pairs of electrons which attack the region of low electron density. So this was very important for us to know so that at the end of it all, when you're doing the mechanisms, because today we're going to look at the mechanisms as we look at these chemical properties. So as we're looking at these mechanisms, we are able to understand where the arrow is supposed to go, from what going to what. You can read for us this statement before you go off. Read for us that NB. Read for us the NB.
In reaction mechanism, arrows move from nucleophiles to electrophiles.
Arrows move from nucleophiles to electrophiles. I think that one is very clear. We are moving from nucleophile, where it is electron rich, to electrophile, where it is electron what? Here it is electron what? Rich. Are we there? While this one is electron deficient. Are you seeing that? So when we talk about the reaction electrophilic, someone is asking, Master, when are we doing synthesis? Don't worry about synthesis. If we study the chemical reactions very well, we are already doing the synthesis. At the end of it all, we can be able to synthesize different substances from different products, from different compounds, from different organic substances. But as we keep on moving, we shall be able to learn all that. Now, let's move faster. Teddy, you have a question. Let me work on your question and then you can move on. Yes, Teddy? I want us to begin, go straight to chemical reactions now. Teddy, you have a question?
No, sir. My question was not about synthesis.
Oh, okay. I believe I've been able to respond to you. So we're going to start with, let's first list all these, the chemical reactions. Teacher, I pray that I finally understand the mechanism. Okay, and Markovnikovs, don't worry. I can see Anita and some other person here, they are worried about the mechanisms and reactions. Today is your day to understand all these mechanisms and chemical reactions for alkenes. And the reason why we have gone through understanding what electrophiles are, what nucleophiles are, is for us to understand where is the arrow coming from, where is the arrow going, so that when we begin these mechanisms, it is not just coming from nowhere, but now we understand why the arrow is coming from this substance going to the other substance. Now, chemical reactions of alkenes. We are going to look at around 1, 2, 3, 4, 5, around 6 reactions we have from A up to F. And number 1, we shall be looking at addition of hydrogen. That is, you recall, we are looking at electrophilic addition reactions, where we are adding electrophiles to alkenes to form saturated compounds. And we shall be able to do the equation plus the mechanism for different reactions. What I want you to do is to make sure that you open up your eyes very well and also have where you're noting down, so that at the end of it all, after this session, there's no question about alkenes that should fail you. That's why I've prepared also a scenario item about the same, that you can be able to take it and you try it out as we move from here. We shall be able to get this document after here. Let's not get worried about anything. Okay, let's move faster. Anita, don't cry about polymerization. It is coming. So addition of hydrogen is also known as hydrogenation. That will be our number 1. Then number 2, we shall look at halogenation, from the word a halogen. So when you say halogenation, there we're adding a halogen. Halogens, we have examples of halogen like chlorine, we have chlorine, we have bromine, we have iodine. All of these are halogens. So we shall be looking at addition of halogen, or what you call halogenation, in the presence of inert solvent and in the presence of water. Someone is asking, what about oxidation? Don't worry. It is on number E. This is also known as oxidation. Then number 3, we shall also look at addition of hydrogen halide, what you call the halogenic acid. That will be another part where we shall be adding the halogenic acids or hydrogen halides. Then number 4, we shall be looking at hydration of alkenes. Hydration is addition of water, but this is acidified water. This is the acidified water. Then E, we shall also look at reaction with potassium permanganate, also known as hydroxylation reaction, also known as, which is one of the oxidation reaction. Then we shall also look at the polymerization. So someone is also asking, what about the ozonolysis? So ozonolysis, we shall also be able to look at it, but of course not today, but we can try it out, ozonolysis. Though on our coverage, these are the major reactions that we are supposed to cover. So what we're looking at are the major reactions that we are supposed to cover according to our coverage. Let's go direct to number 1, addition of hydrogen or catalytic hydrogenation. Let's use only 1 minute before so that I can remove this dot which was put on our screen. Just a minute, and then I bring it back. Yeah, very good. I think it has gone off. we can be able to see what we have on the screen very well. So number one, we are looking at addition of hydrogen, which we have also called hydrogenation, and there is the one catalytic hydrogenation. I want only one person to tell us what you know about hydrogenation. Then we shall write the equations and then we move on. Let me start with Mapel Joseph. Joseph, unmute. I like the way we are participating. Good afternoon. I like the way we are participating and very active. Yes, Joseph.
Master, with
Yes,
the
Joseph.
hydrogenation of alkenes, Master,
Yes,
I'm saying
please.
generation of alkenes. If we had alkenes, we end up getting what we call alkenes, and this is
So
done in the presence of
it is done in the presence of.
alkenes. It is done in the presence of catalyst at a temperature of 140 to 150 degrees Celsius, or it is done using palladium or platinum at room temperature. That is
Oh,
what I
very
know
good.
about hydrogenation of alkenes.
Thank you very much. Thank you. Thank you. You can mute. You can mute. Okay. Thank you. I think Joseph has managed to explain for us very well what hydrogenation is of alkenes. He has told us that in hydrogenation of alkenes, the alkenes are reacting with hydrogen in the presence. Now, he's telling us in presence of catalyst. And this catalyst has given us number one, palladium. Catalyst, he has also given us platinum catalyst, and has told us that platinum catalyst and palladium, they work at room temperature. And then he also talked about the nickel catalyst, and he told us that for it, it works at 150 degrees Celsius. And he has told us that when all this happens, they move from alkenes to form alkenes. We can clap hands for Joseph. He has given us a detailed description of what hydrogenation is. We are going to use an example. Let's have an example. And we are going to use, okay, which example can we use? Ruth, you have, your hand is up. Yes, Ruth. Ruth?
Excuse me. And no, I was just adding on. Okay, I'm also going to give the example, but as adding on what I know about hydrogenation, that each
Okay.
bond, each double bond goes with a mole of hydrogen gas. So if I have
Oh.
an alkene with one double bond, it goes with one mole of hydrogen gas. But if I have an example, okay, that one is the example I'm going to start with is a bit complicated,
Okay.
but buta 1,3-diene will take 2 moles of hydrogen. But the first
Oh,
example I
good.
can give is propene.
Propene, okay. Let's
Yes.
have that. So when you have propene, let me hope that is the formula for propene. Is it the one?
Yes, it is.
We are adding what?
We are adding hydrogen.
Hydrogen in presence of what?
Of nickel catalyst.
Of nickel catalyst. So
in temperature of 150.
50 degrees Celsius. What do we get?
We get propane.
We get propane. So propane. Is that the formula?
Yes.
Yeah. So we're moving from a propene, which is an alkene, and we're getting propane, which is an alkane. I believe that is it. Can you tell us the mechanism? Can you take us through the mechanism of how this one comes about? Luth?
The mechanism. Okay.
Yes.
Let me see. The mechanism. I hope I don't mess up. So no, let's pick another person.
Okay, thank you. Thank you.
Yes.
That was good. Now we can have another person. Samuel. Yes, Samuel.
I'm not very sure.
Okay, Samuel. Okay, Sisi. Sisi.
Yes, teacher.
Yes, can you take us through the mechanism just briefly?
Okay, so I'm going to should I call it spreading the hydrogen bond?
Oh, so you're
Yes.
telling us, okay, one thing maybe what you're telling us that if we have our hydrogen here, this hydrogen, it has two atoms
Yes.
which are bonded by a single bond. Are we there?
Yes.
So what
Yes.
are you telling us about these two hydrogens?
So those two hydrogens are both like, okay, I'm going to pick one. That one will have to go with one of the bonds
But
on
there
the
is one,
propene.
it is partially what?
Partially
One is partial,
positive, then
and then the
partially
other one is partial negative.
negative.
Yeah?
Yes.
Okay,
Then
now
the
we can.
partially positive hydrogen atom
Mm,
will go with one of the bonds in the propene.
in the propene. Okay, thank you. So which means you keep your microphone on. We have, you recall this is an alkene with a double bond, and one is a sigma bond and the other one is a pi bond. Now the pi bond we say it is weak, and therefore it can easily be attacked. It can easily be it attaches because it is weak. It can easily break. So which means what happens, because it is having electrons and it is weak, can easily break, it will break and it comes for this one, which is partially positive, and it will, then you have this one, which is partially negative. And when it comes for this partial positive, this bond also will break and takes off this one, which is partially negative. Are we together there?
Yes.
Sissy, is it what you know? Is the one you are telling us?
Yes, sir.
Okay, good. So which means at the end of it all, we are going to have CH3CH. Now the other bond has broken, and therefore we have remained with a single bond. Yes, Sissy? So
Yes.
where is this hydrogen going to attach?
So that one will have to attach to the carbon that has the highest number of hydrogen atoms.
With more hydrogen atoms. So it means it will go this other side, it gets CH3.
Yeah.
So what will happen? What will happen?
So this carbon that has one hydrogen will have to gain the hydrogen this side that gained the other bond, becoming a full electron.
Okay, but before that, is it because this hydrogen is attaching to this carbon atom? Are you seeing that
Yes.
this carbon is going to remain unstable because it is
Yes.
now attached to only 3 bonds? Are you seeing that? So which means it
Yes.
is lacking, and therefore we put a positive charge. And then plus hydrogen ion. This hydrogen is the other one, this one here. This one which has
Yes.
broken. Are we there?
Yes.
Then at the end of it all, we are going to have this hydrogen come, because it is electron rich, it is going to come and make this carbon atom stable. And then at the end of it all, we shall be having CH3CH. Now this hydrogen is going to come attached to this carbon atom. They become 2 hydrogen atoms. and then CH3. And then we have our mechanism done. Thank you, Sisi, for leading us in that. And next we have
So
anyone with
I'm
a
also
question.
asking,
Yeah.
so isn't it okay, is it optional to to bring back the hydrogen, like the hydrogen and the nickel catalyst?
I've not heard very well. Is it what?
Is it optional for me to show what I've used, like the hydrogen that we use that faster and the nickel catalyst?
You recall here we have
Yes.
just used the hydrogen, 1 mole of hydrogen and nickel catalyst. The nickel is a catalyst. It does not participate in the reaction. It is just
Yes, teacher,
helping to
but I'm
speed up
saying
the reaction.
that the labeling, like the way we've labeled here. Do I
Where?
also label that arrow in the mechanism?
Which arrow here? I'm not understood there. Like
Like
here,
here.
okay, I
Yes.
understand. Are you saying that here, putting now hydrogen, here, putting the hydrogen like that?
Yes. Is it
No.
optional?
It is not necessary. Why? Because up there, you recall up here, you have already written your equation. Are you seeing? You already have your
Yes.
equation and you have shown that you have used the hydrogen in presence of nickel catalyst. So there's no need when you come down here on mechanism, the need of showing us that now here you have used the nickel. No,
Okay.
it is not necessary because it is a continuation from what you had up there.
Okay, thank you.
Welcome, Sarah.
Sir, please pardon some of us.
Sarah, you remain on now. Because today I want us to understand mechanism and we don't have issues again with mechanism. Sarah, are you there?
Yes.
Okay, so we are going to repeat, but using another example. So let's use
Yes.
part B. Which example can we use? Tell me, which alkene do you want us to use?
Butene.
Butene. We but 1 in, but 2 in.
But2 in.
But 2 in. So which means we shall be having CH3, CH double bond, CH, CH, CH3. Is it true?
Yes.
We are using hydrogen in presence of what?
Palladium.
Palladium. Which condition do we use? Which temperature?
Sir, made 100.
Here it is low temperature. But you don't forget that we have talked about this here, that for palladium and platinum, they use room temperature, while for nickel, it is at 150 degrees Celsius. Have you seen?
Yes.
So the first example was for nickel catalyst, and now we are using palladium as our catalyst. So what becomes our product? What is our product now? What is our product? Let's be, yes? This is but 2 in. What becomes our product? Jovi, are you still there? Okay, Jovia has gone. Nyombi, let me move with Nyombi now. Nyombi Imla.
Yes, sir.
Can we move together?
Okay, sir.
So what is our product there?
My product is butane.
Butane. So it is CH3, CH2, CH2, and then CH3. And then this one becomes our butane. Now we want to show how we have come up with this product. And that's what we call the mechanism. Yeah? So what is our first step? I want us to move very fast. We have 1 hour, and with this 1 hour should be enough to finish these reactions. So I want us to move faster.
Now the dissociates to form partial charges, that is the hydrogen partial positive and the hydrogen partial negative.
Okay, very good. Okay, now which means we are having our hydrogen, which is dissociating to form the hydrogen partial positive and then partial negative. Okay, which means I bring our butane, but2 in, like that.
Yes.
What will happen
Then
initially?
we bring the hydrogen, which is partially positive, and it is going to be added onto. Being that it's an electrophile, it will withdraw electrons from the source of electrons there, that is the double bond, and take out, withdraws electrons, and it will be added.
So this one is also going to break.
And that one breaks off.
Oh, my space is not enough. How can I do it? So if I show that it's breaking like this, will it be very clear for us? Or I rub off. Maybe I rub off. Let me rub off this, and then we can repeat it. So we're having hydrogen, partial positive, and then we have hydrogen, which is partial negative. So the double bond is going to come for this one, which is partially negative, and then this bond will also break. Is it?
Yes.
Let's move faster now. So what do we form here?
We form CH3.
We form CH. Is it a
CH3.
full allo or a double allo? So we have CH3, CH.
CH2.
So this hydrogen is going to attach to this carbon atom.
Yes.
So you form a 2, and then you still have a single bond now. CH.
Then a CH, that is a carbocation.
Oh, carbocation. So there's a positive charge here.
Yes.
And
then our
plus
negative
hydrogen.
Nucleophile.
Okay, so what next?
Then that nucleophile is going to be bonded onto the other carbocation.
So it will come and then bonds to this carbocation. And then finally, we shall be having our product as CH3, CH2, CH2, CH3. And that marks the end. Thank you very much.
Excuse me, sir. I'm inquiring about the other first example. And my question is, do we always have to, do we follow the anti-Markovnikov rule whereby the electrophile is added onto the carbon atom that has the higher number of atoms?
Okay. Now, in hydrogenation, that one may not matter a lot, because at the end of it all, you recall it is hydrogen and hydrogen. Are you seeing that?
Yes.
But where we have a hydrogen and another atom, then Markovnikov's rule is going to apply. But now, what will be my advice? My advice would be, let us always follow that. That the one who has is added another. You recall the Bible, it says that for those who have something will be added. So that is Markovnikov's rule. Unless you have a peroxide. If you have a peroxide, that's why we go for anti-Markovnikov's.
Okay, sir. Thank you, sir.
Yes. Okay. You're welcome. Joseph, you can mute. We'll hear from Joseph. Joseph, you have a question?
Yes, Master, I have a question.
Yes, please.
So I was asking,
when
you are dealing with hydrogen,
the problem, your network, Joseph. Joseph, what are you saying?
Things.
Hello? Joseph, is it okay you put that question in the chat? You put that question in the chat. Okay, Vine. Vine, you unmute. Vine.
Yes.
Vine, unmute.
So my question is
Mm.
the movement of the arrows. Like
Tell
for
me.
example, this side where the hydrogen ion is. Like, is it
Yes.
supposed to come from the negative sign to the carbon, or is supposed to come from the atom itself?
Okay. So is it supposed to come from the negative sign or from the atom itself? So whether we put on the atom or from this, what we are looking at is this one is a nucleophile. It is electron rich, is going for electron deficient. Yeah. So whether it is coming from up here or on the atom itself, there is no big issue there. So long as we are showing the arrow, where the arrow is coming from and where it is going. You recall it was our NB here where we said that the reaction mechanism, arrows should move from a nucleophile electron rich, to electrophile which is electron deficient. Are we clear there? Okay. I believe now we can go to something else. Let's go to something else. Dr. Jimmy, if you have something, kindly let's see. Dr. Jimmy, any question? Unmute. Okay, Pauline, do you have a question? Pauline.
Yes.
Yes, where?
Like if it was a buta 1,2-diene, how could you do it?
Now, if it is buta 1,2-diene, meaning the number of molecules are going to change. Okay, that's like this. You're saying buta. This is 2 double bond CH CH. Now, if it is butane, which means the number of please, you're in a noisy place. You're in a noisy place. You're in a noisy place. Okay, Pauline, you are in a noisy place, but I believe when it is buta 1,2-diene, meaning there are 2 double bonds. Someone talked about it at the beginning of this session when I'm looking at chemical properties, and we say that each double bond, it takes 1 mole of hydrogen. Now, since there are 2 double bonds, meaning we are going to need 2 hydrogen atoms, maybe in presence of nickel catalyst at 150 degrees Celsius. There will be 2 moles of hydrogen, because 1 mole of hydrogen will be taken by 1 bond here, then the other one will be taken by this one. I believe we are good to go. Martha, if you have a question, and then we can move on. Martha. Martha, unmute. Angel Maria.
Teacher,
Yes, please.
I want to know why is it a reversible reaction as we're heading to the second step during the mechanism?
Oh, so you'll find that most of the time you'll find that in the reaction that we are carrying out, there's where we're having a reversible, and then there's where we're having a full allo, especially when you're coming to the final product. So when we show that it is a reversible, meaning that the one we have formed, it can easily go back to the where we are coming from. It is reversible. Like when you add the other one, it can easily go back. Then there is where we go to the final product. That's when we normally use a full allo. But those double allos, they are meaning that it is reversible. That intermediate product we have formed, it can still go back. Is it clear?
So teacher,
Yes?
sorry to
Teacher,
interrupt, but does it mean that we have to cram the compounds, the alkenes that are reversible, that have an intermediate, okay, that an intermediate that can go back to the alkene?
Oh, no, you don't need to cram. You look at this intermediate part here. Are you seeing it?
Mm.
So here, the bond has broken to remove the hydrogen, which is electrophile here, and then the other one is breaking down. Is breaking to form this ion here. So when you come on this one, you see that this, when you get this plus the other, like when at this point we can have this one coming back to the other initial uh, initial initial compound that we have. That is, if this hydrogen is removed, the one we have added. So when we put intermediate, those intermediate compounds we are having in there, we use the double alloys. Even when we move on, we are going to see that there are some areas where we shall keep on using the double alloys, but when you come to the final product, we should find that we are using a full alloy, but for intermediate, meaning that the other compound can easily go back to the initial product. Because that
So
is the reason why.
does that mean from maybe a compounds of 4 carbon atoms and above, we expect to have them a bit, okay, reversible in their intermediate state, and then
No,
probably from propene
no,
downwards?
no, you see even the one for propene, at first I had not yet, but we collected
Okay,
it.
yeah,
Have
I've
you
seen
seen?
it.
Yeah,
Yes.
we collected it, yeah.
That means all of them are at the
Yes.
intermediate state, they can reverse back. Okay, okay, teacher.
That's the one. Okay, now let's move very fast. I see time is running and we may not finish. Halogenation, addition of halogen. And now we are talking about in presence of inert solvent. Which inert solvent we normally use? Are you still there? Okay, let me have one person I can move with. Who is ready?
Yes, teacher.
Okay, Ruth.
Yes, teacher.
Ruth, are you ready? Let's move
Yes.
together. Do you know something about addition of halogen in the presence of inert solvent?
Yes.
Give me an example.
Okay, so when alkenes of room temperature are treated with halogens, that is chlorine or bromine in an inert solvent. Inert solvent is, for example, carbon tetrachloride.
Okay,
The
I'm going to put an
halogen,
example. So we are saying, which halogen can we use?
we're using, okay, let's use chlorine.
In presence of inert solvent, we said carbon tetrachloride.
Chloride. The
Okay.
halogen rapidly adds across the double bond to give corresponding the double bond.
To give a corresponding what?
A corresponding vicinal dihalide.
Very good. That is nice. So, which means the chlorine atoms are going to attach themselves to this across the double bond. So this carbon atom takes one chlorine atom and the other one takes another chlorine atom. That is nice. Now, without wasting much time, can you take us through the mechanism?
Okay, so polarizes hydrogen. Okay, that inert solvent polarizes the halogen. So we have it dissociate. Let's use dissociate to partial negative and partial positive. So chlorine.
Okay. So chlorine is okay. Let me rewrite this. Propene. And they're saying that chlorine is partial positive, and then you have
positive and partial negative.
negative. Okay, so what happens?
then okay, one bond, which is the pi bond, dissociates or breaks and goes to the chlorine atom, the chlorine. Then we have the pas the okay, another arrow.
This
This
one will
side
also
up.
disappear.
Yes, that one will disappear.
Okay.
Then we now have our alkene again, but with this other chlorine that was positively charged attached to it, to
Okay,
one
so
of the
where is
carbon
this?
atoms.
This chlorine atom is going to attach to which carbon atom?
To carbon atom 2.
Which one?
The second one. The second one. Carbon atom 2.
This one.
Yes.
So you're saying we put it here.
Yes.
Then what will happen to this carbon
Then
atom?
that one, it acquires a positive charge.
Positive charge. Then
So
also
then
we have this one
we
which
add
draw, which means we will have a
chlorine
negative there.
ion.
Okay.
Yes. Then we finally move. Okay, I saw you do it in the previous one, though I don't have it here. But you carried this. Okay, let's let me use the method I know. The next arrow.
The next arrow here.
Right under and under. Just straight.
Like this?
Vertical. Yes. It gives you, we're going to have a vicinal dihalide. So we'll have that chlorine, then a chloride ion attached to where we saw that where the carbon atom is positively charged. There.
Here.
Yes.
No, so what is causing this one to come here? So you're telling us that this one plus this one, it gives us this product. We don't need to show the arrow.
Okay, so for us we did not show it, but okay, let's indicate the arrow. From the chloride ion to yes.
It's all right. That is nice. Anyone with a question? And I believe since we know this, and what if someone at the first point, what if this chlorine was put on this first carbon atom? Ruth?
Yes, teacher.
What if?
If that chlorine was put on the first carbon atom, then for the case of propene, then the positive charge would be on the second carbon atom. So we'll have, I'm thinking, I'm not saying the right thing. We'll have the chlorine atom, the first one, which came from the partial positive charge, attached to that first carbon atom. Then at our last point, we'll have the last chlorine that forms the vicinal dihalide forming on the middle chlorine atom.
Meaning we could be having something like this, plus chlorine ion, and then finally we'll still come back here.
Yes.
And what is causing it to come there is this one, which is going to come and attach on that. Yeah?
Yes.
Yeah, so here we are just looking at an alternative. Someone is using this direction, and then the other one has used this other direction. So for this one, we may not have any issue because we are adding chlorine atoms. It's the same case we had even on hydrogen, addition of hydrogen. But we shall see where it matters a lot, especially when we come to those ones which involve like hydrogen atom and any other atom.
The mechanical.
Where that one is going to be applying. There are those people who had issues with mechanisms. Are we seeing that now things are becoming much easier? Let me know in the comment section whether we are now becoming much better or we still have some issues with mechanism. Today, I want us, by the time we finish this, let it be one of the way or one area that we enjoy if they talk about mechanism. Mugisha Henry, what are you saying? Mugisha Henry? Mugisha Henry?
Yes, sir.
Yes, please.
I is it compulsory that the inert solvent should be carbon tetrachloride?
It's not compulsory, but if we have another, that is the common inert solvent that is used. Yeah. But if we have another inert solvent, we may apply it. But the question is, what if you use the one the examiner doesn't know? Are you saying that? So it's better we use the one which is common to each and every one. So carbon tetrachloride is one of the common inert solvents that are commonly used. That's why even us today we said, let's use that one because it is the common one. Yeah?
Okay, I get you, sir.
Now remain on the call and then you take us through addition of halogen in presence of water. We are still on halogenation, but now this time round is in presence of water. Okay, tell us.
So they are in presence of water, I think, but I'm not sure. There,
So, and I want us to use this one, butene, but1 in. We are having, maybe now we can use bromine. Can we use bromine or chlorine? Okay,
bromine.
let's first use chlorine. Chlorine in presence of water. The other side, it was in presence of carbon tetrachloride, which is a inert solvent. Now, this time round is chlorine. What is the product first?
Then the product is
What is the product? Hey, what
one,
is
two.
happening?
It's 1, 2.
Okay, maybe tell me. CH3, CH2, CH. What attaches here? CH2, what attaches here?
On the first chlorine, in the first carbon atom, that one, there will be chlorine.
Chlorine. Then on the second here?
OH.
OH. Which name is given to this compound?
1 chloro.
1 chloro.
2.
2.
Butol.
Yes?
Butol.
2 butol.
Yeah.
Or we could say maybe 1, 2, 3, 4. Since the because this is an alcohol, yeah? Because this is an alcohol and it is on carbon 2, then you can say butane, maybe butane 2 on. Yeah? Yes, butane 2 on. This is B. Let me hope it is clear for everyone. Thank you very much. Now we run to mechanism. Do you think you can take us through mechanism or we call someone else?
I can try.
Okay, let's begin.
So there will be reaction. Chlorine, we are going to react with water.
Okay. So chlorine is going to
react.
Aqueous reacting with water. What will it form? Getting what?
Hydrogen chloride.
Hydrogen chloride. Plus.
Then.
This one?
Water. Really? Yeah.
Yes?
I think that's, yeah.
Okay, so you need to know the name, hydrogen chloride. And then, so what will be the next step?
So we are going to get that butene. We
Butane.
add it. Hmm. We dissociate chlorine. Yeah, so we get the hydrogen chloride.
This one.
Yeah, we dissociate it.
When you dissociate hydrogen chloride, what do we form?
We get hydrogen proton and
Do you think, are we going to dissociate the hydrogen chloride? You recall our product. Our product is having OH. It is also having the Cl. So if we go for HCl, it is going to become a challenge. Instead, now we can come to dissociating this one for the other, for this one, for HOCl. But now, when they become polarized, what happens? Which one becomes partially positive and which one becomes partially negative between OH and Cl?
OH becomes partially positive and then Cl becomes partially negative.
Partially negative and then partially positive. And then what will happen? So you're saying that OH, then Cl, this one becomes partial positive, and then this one becomes partial negative.
So those double bonds will give electrons to OH.
Okay, then this one will break.
Yes.
Then what will be formed?
Are going to form CH3, CH2, CH, CH2, then OH.
Then OH. But you recall your product you have.
So maybe if we don't, yeah. Sir?
Yes.
Maybe if we don't follow the Markovnikov rule, there they are
Because
going to put OH.
Which means your OH will put it here, and then here becomes a cation.
And yeah.
And then we shall have Cl. Okay. And then finally, we shall be having CH3, CH2, CH, OH, and then we have CH2. Now this one is going to come and attach it to that carbon atom, and therefore you shall be having Cl. So that was your first method. But also we can use the second method, this one, where we don't need to first react. Now we have CH3, CH, 2, CH, double bond CH2. So we have bromine and water. So since we have bromine, is it bromine or chlorine? We have chlorine,
yeah?
We are using chlorine. So the chlorine when dissociates, becomes partial negative and also have partial positive. So what happens? This double bond will come and comes for this partial positive electrophile, and then this one will also break. And then here we have our intermediate here, CH3, CH2, we have CH single bond, CH2, and then we have Cl. And then this carbon atom becomes a carbocation. And then we have plus Cl. But now you recall in the solution, we have a nucleophile of water. And you recall that this water molecule has this lone pair of electrons. So these lone pair of electrons are the ones which will come and now attack. Because you recall the allos always move from the nucleophile to electrophile. So when that one comes, still this one now will be a partial allo. So this will be CH3, CH2, this will be CH, then here we have OH2. But now oxygen is having more oxygen atoms. Are you seeing that? It's having oxygen atom. Therefore, here we have it will be positively charged also. And then you have CH2, then you have Cl. So for us to make it stable, we can say we remove a hydrogen ion. But remove it, so it becomes stable now with CH2CH, and then here you have OH. Here we have CH2, and then you have Cl. Is it clear?
I get you.
Thank you very much for reading us in the first method, and now we have gone through the second method. If there's any question, someone can ask, but if not, then we can move on. Please, if you don't have a question, let's put down. Sis, there's Ashanti. Okay, Ashanti is put down. Sebaiya. Yes, Sebaiya. Yes, please. Yes, please.
Does the arrow attach exactly to the atom example? Yes, teacher.
Does the arrow attach? Now, are you meaning like here when the arrow is coming from the double bond coming to this?
Yes, teacher.
Oh, now, maybe let me rub off this. Okay, so the arrow is coming from the double bond, yeah? Then it is coming to this. It can be very close, even if it doesn't touch, but it can be very close, like that. But not putting it very far. You have seen some people, some learners, you find they are now doing it in this manner. They do, and then they reach it there. Now that one, when I'm marking, I will not mark that. So let it be closer, let it come closer to that atom where it is going. Where is it coming from? Let it be very clear. So it is very good for us to be very clear when we are showing where the arrows are going and where it is ending. So here you will reach it there, and it is not touching there, but it's very close. If you're not very keen, you may think it has touched, yet it has not touched there. So it will be very close, and such someone who is squaring you is able to see the arrow very well.
Oh, thank you, teacher.
Now remain on the call, and then we go to what people have been asking. The hydrohalogenation. Now, hydrohalogenation is the one we call the addition of hydrogen halides. The one I also called at the beginning the halogenic acids. So these are the halogenic acids, the hydrogen chloride, the hydrogen bromide, the hydrogen iodide. And we are saying that it is addition of these hydrogen halides across the double bond. Now, in this case, where we're having a hydrogen atom and another atom, we are saying the Markovnikov's rule applies. What are we talking about when you say Markovnikov's rule? So Markovnikov's rule says that the hydrogen attaches to the carbon with more hydrogen atoms. For example, if you look at this example here, it is a propene. This is propene. It has a double bond. We have this carbon atom and this carbon atom. We can see that this hydrogen on the halogenic acid, the hydrogen bromide, when it was attached, at first it was attached to this carbon atom with two hydrogen atoms compared to this one. So we see that they became three. And then bromide, it came on this second carbon atom. So which formed two bromo propane. Two bromo propane. So that is the one that we are having. And now we say that also, if we don't use Markovnikovs, there is what you call anti-Markovnikovs, not anti, but anti-Markovnikovs. The anti-Markovnikovs, this one works if there is a presence of a peroxide. When the peroxide is present, like an organic peroxide, sometimes we can always label it with this, but this can be an alkyl group and this another alkyl group. But if there's presence of any peroxide, then we use what you call anti-Markovnikovs. Now, when you say anti-Markovnikovs, is now the opposite of the Markovnikovs rule, meaning now the hydrogen will attach where there are less hydrogen atoms. We are going to do some practice items as we go through this. But as I said, this is the one we're calling the hydrohalogenation, or what you call addition of halogenic acids or addition of hydrogen halides. Azendi, you have a question. Let me have Azendi. Azendi, unmute. Azendi. Audrey. Audrey.
Good evening.
Yes, Master.
Now let me have one person start, then the other one will follow.
Let Azendi first start.
Okay. Who is starting? Azendi, are you there? Azendi? Okay. Audrey, take us through. Audrey, unmute.
Saying good evening, teacher.
Good evening, how are you?
Fine, thank you. So as inquiring to note that if the anti-Markovnikov, like is anti the reversal of Markovnikov, since like
Yes.
Markovnikov deals with like attachment to the ones with the more hydrogen atoms. So that means anti-Markovnikov, we are attaching, let's say our
Hydrogen.
the neutrophile that is negative, partially negative, will be attacking the ones with the carbon atom with the less hydrogens.
Yes. So the hydrogen, when it is anti-Markovnikovs, the hydrogen now attaches the carbon with low hydrogen or less hydrogen atoms. So it is the opposite of the Markovnikovs rule. And we're going to have an example. We're going to have two examples. The one which is clarifying on Markovnikovs and the one clarifying on anti-Markovnikovs. Now, if you're still there, I want you to...
Teacher, I'm still inquiring on a little something. You know our previous examples where we had like but2-ene and everything. We were also attacking the ones with the more hydrogen atoms. So are we still following what Markovnikov's rule, or Markovnikov is followed in specific in examples, if I should say?
Now, Markovnikov's rule, you'll find out that we are applying it in the examples or in the reactions which involve hydrogen ion. Maybe it can be hydrogen with another atom. Maybe it can be hydrogen and water. It can be hydrogen. Like when you see the rule, the way it states, it is specifically talking about a hydrogen. Maybe let me state for you. It states that when a molecule containing, you listen, when a molecule containing a hydrogen atom is added to an unsymmetrical alkene on a carbon atom carrying a functional group. Are you seeing that? So And Markovnikov's rule applies if we're adding a substance which consists of a hydrogen atom. Now, for the previous one, like the one we are having for halogenation, we are adding only chlorine atom or bromine atoms. Those are not hydrogen atoms. In those compounds you're adding, there's nothing like hydrogen. So anti-Markovnikovs may not work. Markovnikovs may not work. But as I said, for us not to have very many things in our mind, let us use that one. If we are also adding like chlorine and we're adding it to maybe this compound here, we can use that. The one which is having more, we give it first. The one which is having less, it comes later. You get? So that we don't always confuse ourselves in one or the other, that have I applied Markovnikovs or I have not. So that's why I was trying to tell someone who asked that let us have that one. But for Markovnikov's rule applies if we're adding a molecule which has a hydrogen atom. And it normally applies if the compound we are working on is unsymmetrical. Do you understand when we say unsymmetrical?
Teacher, I can talk more about it.
Yeah, unsymmetrical, you call, when you talk about symmetry, lines of symmetry. If you talk about lines of symmetry, like for this triangle, which is having two sides which are equal, how many lines of symmetry can we have? Are you seeing this line of symmetry?
Yes.
So what does it mean? It is going to have, this side is equal to the other side. Are you seeing that? So when you say symmetrical and unsymmetrical. So when you say symmetrical, for example, butene, we can have but2 and but1. So but2 becomes symmetrical. You look at this. Where the double bond is, what is on the other side is the same as what is on this side. So we say this one is symmetrical. But when you come to but1, it is CH3, CH2, CH, double bond, CH2. Now this one, you say it is unsymmetrical because when you look at what is here, is not the same as what is on the other side. Have you understood that?
Yes.
So we say that for Markovnikov's works on symmetrical alkenes, while for these ones which are symmetrical, you call this carbon atom and this carbon atom, they have the same number of hydrogen atoms. So when you are adding, it can add on any side it wants. Are you saying why it does not apply on symmetrical? Have you made some analysis on that now?
Yes, but teacher, you said Markovnikov's applies on those with symmetrical.
No, it applies on those which are unsymmetrical.
Oh, okay. Now I understood, even with the definition of Markovnikov's, because it will be attached to the one with the H2 instead of the
Yes, very good. But now the one which is symmetrical, they are the same, so there's no carbon atom with more hydrogen atoms. Have you seen?
Yes.
Time is not our friend. I would like us to move a little bit faster. So let's have an example, and we are going to apply Markovnikov's. Can we move together? Because of time, we move very fast. Audrey, are you still there?
Yes, teacher.
Which example can we use? Let's be faster.
The other one of but2 in, CH3.
Okay, let me first give you mine. Give me the name of this. Give me the name of this compound. What is the name of this compound? Get for me the name. And then after that, you tell me the product it forms. Okay, before you put the product, before we name it, can you give me the product? Just read for me.
CH3.
Let's be fast because of time.
Okay. CH3, the other methyl group.
Hey,
No.
where are you?
I'm here.
Audrey?
Yes. Hello? Hello? Can you hear me?
It has a problem with this network, I think.
Okay.
Because you're clear.
Okay.
Let me see. Teacher?
Sorry about that. Audrey, are you still there?
Yes, teacher.
Okay, you are still taking us through. Let's is running. Yes, please.
I'm trying. I'm not so sure about the product, but CH3, C with the methyl group, then and you're going to have also the bromo on that same line. Then you're going to have CH2, CH3.
Okay. So which means we are having CH3, CH3, C. So what do I put here?
I'm thinking of the methyl and also the bromine group.
So the bromine group goes here.
Yes.
Then C H here we will get how many hydrogen atoms?
2.
2 CH3.
3.
Okay, that is good. Yeah, I believe in that case we have considered some people have started disturbing our screen. Okay, I think it's better now. Okay, now you're going to continue to take us through the mechanism now. The mechanism. Other members, you can start writing for us in the chat. Tell us the product. Which name can we give to this product? What's the name of this substance compound which is reacting? So I need the name of this and also the product in our chat section. Now let's move very fast. Markovnikovs. Our time is running.
So do you want me to say the name of the compound?
Okay, what is the name?
I'm thinking 2-methyl but2-ene.
It is?
What I'm thinking is 2-methyl but2-ene.
2-methyl but2-ene. Okay. 2. Okay, let me write here. 2-methyl but2-ene. I believe that is true. Yeah. Because when you count from this side, this is carbon 1, carbon 2, carbon 3, carbon 4. On carbon 2, you have a methyl group. On carbon 2, you have a double bond. So that becomes very correct. And then the product?
2 bromo, 2-methyl butane.
2-methyl butane. Very good. Yeah, that is nice. Now the mechanism. Let's move very fast through the mechanism.
So you're going to write the compound 2-methyl but2-ene.
It is there.
You're going to show the structure of hydrogen bromide, like that bond between hydrogen.
Which one is partially positive and which one is partially negative?
The bromine is partially negative, and then the hydrogen is going to be partially positive after the double bond attacking the hydrogen atom.
So this one will attack, and then this one will go off. Then what do we form?
So you're going to form a cation, of which it's going to have the CH3.
The cation is on which carbon atom?
On the second one.
On which one?
That
on this one?
there, the one, yes, that one.
Okay. Then this hydrogen is going to attach on this.
Yes, on carbon number 3.
Okay.
Teacher, why do you have reversal arrows?
We say that here we are having intermediate. So the final product is when we put our full allo. That's when you can have a full allo on our final product, when you are coming to the final product. Because here we are forming an intermediate product. This is not a final product we have. It is the intermediate product that we are having. So that's why it's very appropriate for us to use those double alloys.
Okay. So the bromine is going, the bromine ion, an ion of bromine is going to attack the cation, hence giving you the 2-bromo-2-methylbutane.
Okay. So in simple terms, maybe I can show it by bringing. So in simple terms, you're going to have this come on the carbocation, and then you'll be able to form this C product. That is very nice. So this is looking at the Markovnikovs, yeah? Are we there?
Yes.
So now let's look at the anti-Markovnikovs example of anti-Markovnikovs. Anti-Markovnikovs. So we say that anti-Markovnikovs, it works if there is presence of what? Of a peroxide. So we can have maybe this propene, and then we're adding in hydrogen bromide, but now in presence of a peroxide. So what will be our answer, since it is anti-Markovnikovs?
One bromo, like CH3.
CH3.
CH2.
CH2.
CH2, then the Br.
CH2 and then Br. Have you seen that if we had used anti-Markovnikovs, it could be a different product. But because we're using the Markovnikovs, now we can see the product that we are having. Have you seen? Because for anti-Markovnikovs, this hydrogen atom could have attached itself here. But now you can see it is attaching on this carbon atom. It is opposite of what we did the other side. So this time round, we use the anti-Markovnikovs. And don't forget, in anti-Markovnikovs, for it, we use the free radical mechanism. Do you recall that?
Yes.
The free radical mechanism. And since we have a peroxide, which means this peroxide is going to undergo what you call the homolytic fission. Homolytic fission, where the bond is broken and they share the electrons. Because a bond is having a pair of electrons, so when they break, this one will go with a lone pair of electron, plus also this one goes with a lone pair of electron. And then, since we have HBr, hydrogen bromide, so we shall also have hydrogen bromide, which is going to combine with one of these products that we have here. And then, of course, we can show, okay, maybe let me remove this. So this one is going to undergo homolytic still. This one will break homolytically. And then finally, we shall be having hydrogen with a free radical. Is it hydrogen? Oh, sorry. So we're having hydrogen. No. We can reverse this. Sorry. Since we have hydrogen bromide, we can have the bromine, and then the hydrogen. Even if we reverse it in that manner, no issues. So we shall be having also one of these OR, and then they undergo the homolytic fission, and then that we can be able to get one of the bromine radical. So which means in this case, we shall be having the bromine radical, and then we shall be having HOR. Because when this one comes and joins with the other one, they form a bond. One electron comes, another electron comes from here, they form a bond, forming that full substance. Okay, then someone is raising up the hand. Let me have them. Pauline, you can unmute and tell us. Pauline, as we move on, you can unmute. Okay, as Pauline is opening. So at this point, after you recall in free radical mechanisms, we have three stages. With stage one is the one we call the chain initiation. From the chain initiation, we go to what? We go to chain propagation, and then you go to chain termination. So those are the three stages that you always have during the free radical mechanisms. So that's initially, this is the chain initiation where these reactants first do react to form those free radicals. And now we want to go to chain propagation. Now in chain propagation is where we now increase on the chain. We are going to expound on the chain, and therefore we are going to be having our propene CH3, CH2, and then it is going to bond with this free radical of bromine. So this one is going to bond here. This bond, the pi bond will break homolytically still, and when it breaks homolytically, we shall be having CH3, CH with an electron there. Now we have remained with a single bond. Then CH2. Now bromine has attached on this one. Then we can keep on moving. At that point, we can bring back this product that we have, CH3, CH with an electron, then CH2 and Br. Now we bond it with our hydrogen bromide, Still, they will undergo fission. This one will break homolytically. So when this one breaks, we shall be having CH3, CH. Now this one, this hydrogen is going to bond with this carbon atom which had an electron. So which means that you're going to have two hydrogen atoms. Then you continue with CH2, and then you have Br plus a free radical of bromine. So at that point, we already have our product we have been looking for. And all this was our initial stage, chain initiation. This is our chain propagation. And now let's look at termination. In chain termination is where we now bring all these free radicals and we combine them together. So we shall bring back our free radicals here, or R, and here we use full alloys. They are forming back these ones. So we have that one. We also have this free radical Br, and then they'll be able to form Ala or Br. And then we call it our mechanism. We already have our product, which is here. Unless there is a question, I'm seeing our time is fast spent, but don't forget initially when you're beginning this lesson, we missed out some few minutes, which I believe you can use to accomplish our mechanisms. But let me hear from us, which questions are we having? And then we can move on. If you don't have a question, we put down the hand. If you have a question, let's keep that hand up so that I can be able to hear from us. Okay, anyone with a question? Okay. Okay,
Teacher,
let me
for me, I
see.
have.
Who is that? Ruth. Yes,
Teacher,
Ruth.
it's Ruth. Teacher, me, I'm sorry, Vanang. Can you backtrack? You've already explained, but I was so much left behind. Once I did not understand, because even in class I didn't understand that rule. Makonikov. From the rule, the adding, you said we add on the one with more hydrogens, but then as if I don't know. So as I didn't understand that everything below has just been off for me. So just begging your pardon on that part, just that first equation part.
Look at that. Let's move together.
Yes, teacher.
Are you seeing our initial compound?
Yes, I am.
You can see even where we have the double bonds, isn't it?
Yes, yes.
Now, you look at those carbon atoms. There's this carbon atom here and this carbon atom.
Yes.
Markovnikov's rules, it says that if you're adding a molecule which consists of hydrogen atom, then the carbon atom with more hydrogen atoms is the one which the hydrogen atom from the molecule attaches to the carbon atom with more hydrogen atoms. Now, between these two carbon atoms, let's call this number 1 and number 2. Which one has more hydrogen atoms?
Number 2, number 1.
Look at number 1. Number one is here. This is number 1 here. We have just named them. Between
number 2.
So number 2 has one hydrogen atom, while carbon number 1 here, it has no hydrogen atom.
Yes.
Now, so for Markovnikov's, we are saying that because this is a electron rich, the double bond, our pi bond, we say it is weak and therefore it easily breaks. So it is going to break and comes for electrophile here, which is the partial positive hydrogen atom. Now, when it comes for this hydrogen atom, now the question is, where is the hydrogen atom going to attach? On the carbon 1 or carbon 2?
You said carbon 2.
So it will be carbon 2 because it has more hydrogen atoms. Are you getting that? Loth? Loth, are you still there? Hello? Hey. Loth, what is our challenge? Okay. So the hydrogen atom is going to attach on this second carbon. And now that's why we're saying that on this second carbon atom, we are having 2 hydrogen atom, and then this one remains with positive charge. Plus the Br, this one which is breaking from here. And then finally, it comes to make this one stable, forming our product. Ruth, are you still there? Okay, Ruth went off. Angela Mariam. Angela Mariam?
I have not understood on anti-Markovnikov.
On anti-Markovnikov.
On the third
Okay.
step.
Can I take you through? Leave your microphone on. Now, on anti-Markovnikovs, we say that for anti-Markovnikovs, it follows a free radical mechanism. A free radical mechanism, a free radical mechanism. And we are saying that a free radical mechanism, it undergoes 3 steps. 3 steps. And step number 1 is chain initiation, chain propagation, and chain termination. In chain initiation, this is where the reactants start undergoing the fusion, the homolytic fusion. They start the reaction of the reactants, or when they break down. And here we see our peroxide undergoing homolytic fusion, and also the product reacting with the reactant hydrogen bromide. That is chain initiation. Mariam, are you still there?
Yes.
Now, let's go to step number 2. Step number 2 is chain propagation. Like from agriculture, I'm not a good agriculturist, but when you talk about propagating, I think we're adding something maybe from another species to another substance, to another crop maybe. Propagation. So even in chemistry here, when we talk about chain propagation, we're increasing on the chain in simple terms. So here, what is happening, we are bringing our original substance, which is propene, and now it is reacting with one of the radical, the bromine radical, and it's forming, of course, it is going to undergo homolytic fusion, and now this bond, the pi bond, is the one which is breaking. So when it breaks, this bond is breaking, one electron is going to come and bond with the one for bromine, and this bromine is going to attach on this carbon atom, and then it will leave this other carbon atom unstable. Or, okay, not unstable, but it is going to leave the free electron on this carbon atom. That's why we're seeing a free electron here at this point. Now, this compound that we have formed, it is still continuous. We are in propagation. So this one, our product here, still undergoes another propagation by reacting with original reactant, hydrogen bromide. So this electron combines with this hydrogen, the bond which is attaching hydrogen to bromine, it blocks homolytically. And then it bonds, this hydrogen is down. Now this hydrogen will attach CH2. Initially it was CH, but this hydrogen is the one which is coming to attach and then becomes CH2. And then finally, we have our product that we have been looking for. What remains in the chain termination, where the free radicals combine together to form back the original substances. Are we clear there?
Yes.
Okay, thank you. You can mute. Then we have Manuela. Manuela? Manuela.
Yes, teacher.
Yes, please.
My question comes on this thing of termination.
Okay.
You said we get back the original compounds, but
listen. We form back original compounds and also we form neutral compounds. Yeah.
How do you know?
That's the one. Neutral compound. A neutral compound, like they are not having, like this one, it becomes a neutral compound, is not having any free electron because this one electron here and this one electron here, they combine to form a bond. So they are neutral compounds which are being formed, and here we have formed our original compound that we had. So that's what happens in chain termination. Are we okay there? Okay, good. Now we put down the hand. Let's put down the hand. Matthew Tonics. Matthew Tonics.
Excuse me,
yes,
sir.
Yes, please.
I would like to know if, because for my head that they only terminate bromine, not this organic peroxide?
Yeah, no. Like what is essential? Some books will find that they are only doing the last one, but you call in termination. We are just bringing back these free radicals. We join them together to form neutral compounds. So even if you add the other one for peroxide, no issues.
Okay, thank you, sir.
Okay, welcome. Lillian. Lillian?
Excuse me, sir.
Yes, please.
Does it mean that we use 2 moles of hydrogen bromide? Because
2
in step
moles.
4, yeah.
Because?
Here on step 4, I'm seeing another hydrogen bromide.
Or another hydrogen bromide. On this one, the one which is reacting with this. Okay, in the solution, we believe we don't need to show in the equation here. We don't need to show that we are using 2 moles. Here, when we come in chain initiation, we are trying to show what happens during the reaction, that these ones are fast breaking, the reaction between the two, but in the solution we have more. So we don't need to put a 2 here on hydrogen bromide. It is not necessary on that.
Okay.
Okay. Mogisha? Mugisha
Thank
Henry?
you. Yes, sure.
Yes, please.
So on the second equation, seeing the HOR, but on the termination step, I'm not seeing it. Where has it gone?
No, here you're seeing HOR. But on termination, you're not seeing what?
I'm not seeing it. Where has it gone?
No, on termination, we are just looking at this. We are bringing back these free radicals and then just joining them together to form neutral molecules. It's not a must that now we have to form every substance that we had initially here. No, it is not a must that you're going to have these ones. Yeah.
I get you.
Okay, thank you. But we need to try out more so that we can be vast with all this. We are borrowing a few minutes and we end. Let me hear from Sebaya Baswan. Sebaya Baswan?
Teacher.
Yes.
Like when on that antimaconikoffs, there is where we were splitting hydrogen bromide.
Yes, here.
Teacher, I'm confused on these arrows. Why are you not joining them from this radical to this bond of hydrogen bromide?
Like this. Do you recall homolytic fission?
Yes, I recall, sir.
Okay, so you're saying that, like for example, are you meaning like these ones, these ones here?
Yes, teacher.
Now, when this one comes here, and then this one will bring it here, it means that we are bringing 1 electron on from here, and also 1 electron from this bond to form a bond between hydrogen and OR. That's why they form a full molecule here. So when this one comes and this one comes, it is half and the other one is half, forming a full bond. So there's no need of squeezing them together, but what we want is to see that this one is coming and the other one coming, they are joining to form a single bond. Are we there?
Oh, teacher, so I should not join them?
You don't need to join them, but they can be closer to one another, close, but not joining them to become making them one, but they can be close to one another.
Okay.
Naftali Ham, finally, Naftali should be the last.
Okay, sir. Thank you. Thank you for the lesson, sir. Now,
You're
for me, I'm asking, you say that at the end, we have to do what? We have to put the full arrow Now why are we using the half alloys?
Oh, you remain on the cone. Are you meaning on this antimaconicals? Hello, Naftal. Naftal has run. Naftal, unmute, please. I don't want us to go with the question. Naftal?
Yes, yes.
Are you meaning on the antimaconicals?
Yes, yes.
Antimaconicals, you see, we are using half alloys, yeah? Half alloys, half alloys, half alloys. But when you come to termination, that's why we're using full alloy.
Okay.
Yes.
Thank you, sir.
Welcome. Now,
thank you, sir.
Before we move any further, look at the two equations which are remaining, which I believe I can leave you to try out. We are remaining with hydration. To prove that you have understood, you recall hydration or addition of acidified water. You're going to try out this one which I want to give us. You're going to try out this. Put it down and you try it out. Reaction of C propene, CH3, CH double bond, CH2. Now hydration, we are just adding acidified water. I think this should be one of the simplest reaction and mechanism that we can do. So let's try that. Then we have also this. Hey, sorry, let me also add CH3. So here you're going to do what you call, you complete the equation and you write the mechanism. I believe we are getting, I'm going to share this one with this question. But these questions in the PowerPoint, which I'm going to share with you, these ones may not be there. So let's note them down. Let's note these ones down. These two questions, you're going to add them. This is addition of acidified water or addition or what you call the hydration. So you're going to do complete and then you do the mechanism. Then the last one is, not the last one, we still have two. The second last one is reaction with potassium permanganate. And this is one of the one we call also the oxidation by addition of potassium permanganate. So we can also try it out. Because of time, I may not complete it now, but let's try it out. Potassium permanganate in the presence of OH, aqueous. So you complete it and then you also write the mechanism. We can also try out part B. These ones, let's note them down. These ones, I expect you to try them out. We have an alkene. My handwriting may not be nice, but I believe we shall be able to see an alkene. We're adding potassium permanganate. Sorry, this is minus. And then you'll put for me the product, and then you write the mechanism. So that is our part A. Then we have part B. That is for potassium permanganate. I know you have them, but now this is for trying out. Hoping that we have noted them down on reaction of potassium permanganate. And then lastly, the last one is polymerization. For polymerization, I'm going to have any ethene molecules. And then in polymerization, we are using oxygen catalyst. And then at high temperature, and also high pressure. As I said, in our next session, those are the ones we're going to start with as we also wind up with hybridization, SP3, SP2, and SCP hybridization. So because of time, of course, we can't go beyond this, but let's try this. Put a product of this polymerization reaction, and then we see how it can wind up. Now, there is a practice item which I have put for last. This is our practice item. I'm going to share it on the group. Let's make sure that we also try it out. This practice item is to help us, help ourselves know whether we have understood this topic very well. And therefore, when you're doing this, make sure that you do it without copying anywhere. First, go through what we have gone through today and the first session we had last week, and then you see whether you can try it out. The question is here displayed on the screen, but I'm also going to share with you the document so that you can try it out wherever you are. You try it out so that next week, or we can even share our responses in the group so that we can be able to check ourselves whether we have passed or not. As I end, as I said, our next lesson, we shall be looking at hybridization in our next lesson, but also completing what we have left out, those two mechanisms and equations we have left out. And also in our next lesson, we shall look at practice items, both in physical and organic chemistry. Otherwise, I want to end at this. And as I always say, let's keep on enjoying the beauty of chemistry. Thanks for attending. And for those who were not there at the beginning, on our first page here, you see that we have the YouTube channel also, Nyirimbebe Isaac Chemistry Connect, where you can always go and you find work that I normally share on the YouTube, Nyirimbebe Isaac. Just type there that name, and then you'll be able to see the channel, and then you'll be able to follow. Let me answer that question, and when you answer that question, when you ask, you're going to lead us in the closing prayer. Let me ZTE, only that person. Unmute, ZTE.
Sir.
Yes, please.
I ask for help here on the question of
on the what?
If
you inbox that question. Inbox it, or your network is not clear. Gilbert, lead us in the closing prayer. Gilbert, lead us in the closing prayer. Then ZTE, you write down that question, and then I can be able to respond to you. Gilbert?
Okay. Almighty Father, we thank you for this day. Thank you for the wonderful session that you have had as we were being equipped with the chemistry knowledge. We thank you for the teachers behind the help program. And I pray that further, as we proceed with our day-to-day activities, you may guide us and keep us safe. In the name of Jesus Christ, I pray. Amen.
Amen. Thank you very much. Have a blessed time. Let's meet again next week as we wind up. May God bless you.